Well, we all know that engines get hot, and we've got to do something to be able to keep the engine from overheating, becoming damaged, and so forth. So what we're going to do for the next couple minutes here is look at, first of all, why we need to cool the engines. We're going to put some numbers in perspective on just how hot an engine gets and how critical it is that we do something to cool the engine off. And then we'll talk about some basic types of cooling systems that we utilize on different engines. So first of all, let's talk about why do we need it? I mean, we know it gets hot, so what? But let's put some numbers on it and give us a real perspective. So here's an interesting graph that actually shows the temperatures, the combustion temperatures inside a combustion chamber in an engine. And we can see that during the intake stroke, my temperatures go down, which is not surprising. I'm bringing cooler air from the outside into the engine, so that's going to cool things off. And then when I go into my compression event, I'm going to get a little bit of a temperature rise there because I'm compressing those gases, and that's going to heat things up. But then I get a real big temperature jump when I ignite the fuel. And we see that those temperatures go up to peaks around over 3,000 degrees Fahrenheit, 3,500 or more degrees Fahrenheit. So we're getting some very, very high temperatures in here. Now let's think about that. Think about what materials that engine is made out of, that combustion chamber, the cylinder walls, the pistons, the valves and everything. What are they made out of? Well, a lot of those combustion chambers, the blocks and everything, are made out of aluminum. Aluminum has a melting point of about 1,200 degrees Fahrenheit. So that's like down in here somewhere. So cast iron's a little bit better. So if we have a cast iron engine, it's about 2,000 Fahrenheit, but that's up here. So that's still way below the peak temperatures that we're seeing inside that combustion chamber. So why doesn't it melt? What's going on? So part of it, there's a couple things going on. Well, obviously, when we get this big high temperature, it doesn't last very long. It's only a very short combustion time. But we also have to actively design into these engines ways for that heat to be transmitted through the metal and out to somewhere else and get that heat away from the engine, or else the metal would melt. I mean, those temperatures in there are high enough that it would cause those metallic materials to melt down. So we have to do something to get it out of there. Here's the other thing to think about how much heat that we have to be able to move. And we talked earlier about the thermal efficiency of an engine. And then we said that of the fuel that goes into the engine, only about a third of it is going to mechanical power. So that's, we talked about efficiencies of 35, maybe up to 40%, something like that. That if you look at the energy of the fuel that's coming into the engine, we're only getting about a third, 35 to 40% out of that engine in mechanical power. So those 2/3 of it, approximately, that are going somewhere else. Where are they going? Well, basically, about a third of that typically goes out the exhaust. So those hot exhaust gases that are going out are taking about a third of that fuel energy out of there. The rest of that, the last 1/3, that is heat in the engine. That is going right into engine components. That's heating up the engine components. I've got to do something to get rid of that. So again, we could put a number on that. So if I have a horsepower, an engine that's developing, let's say 8 horsepower of mechanical power going out. So that means that mechanical power, I got about the same amount of power that's going out of the exhaust stack in heat. And I also have a third of that power that's going heat into the engine component. So I have to have 8 horsepower equivalent of cooling to be able to keep that engine from melting down and becoming damaged. So it's a pretty significant task in terms of designing engines and having the engine operate correctly and at temperatures that are reasonable for us. So how do we do this? There's 2 basic systems. 2 basic ways we can do this. The simplest is just to have an air-cooled engine. This is very common on smaller engines, small gas engines like in lawnmowers and things like that. Motorcycles, this is very common to have an air-cooled engine. So basically, we rely on the transfer of heat from the surface of that engine block and everything of those metallic components. We rely on the air transfer, the transfer of that heat directly to the air. And there's a couple things that we do to enhance this, to make this happen. We know that metal to air transfer, so that surface and that way of transferring heat is not real efficient. It's not real fast. And so if I just made smooth wall cylinders, smooth wall components on my engine, they would not get cool fast enough because there's not a surface area. So what you'll see on an air-cooled engine almost always are these fins. And you notice that on engines that we've torn down. You can see it on motorcycles and things like that. Always have these fins on the side of the engine, like you see here. You can see some more in this picture, these fins on the side of the engine. So these are machined or manufactured into the components, and their sole purpose is to increase the surface area. So instead of a smooth sidewall, I have all these folds and everything in that surface, and so that gives me more surface area where that air can contact the metal and be able to transfer that heat away. So the heat transfers pretty quickly from the inside, from that combustion chamber, out through the metal. It transfers pretty quickly through the metal, gets out to the surface area, and now I got lots of surface area with all these fins to be able to transfer that heat into the air. So then the air can take that heat away. So that's the air cooling, and so that's one of the main things that you almost always see on an air-cooled engine are these fins, these cooling fins. The other thing that we'll commonly do is utilize some forced airflow, typically from the flywheel. So almost all small gas engines that have a flywheel like this, you'll see these fins on the top of the flywheel. And those fins, their purpose is to move some air. So they're just a big fan. So all it's doing is moving air. Now, what will often happen is around that flywheel, we're going to have a shroud or some kind of a shield. And part of the purpose of that shield is to actually direct that airflow. So the air comes out from that flywheel, and that shroud will direct that air around the engine. So the idea is that it's going around the engine, and it's grabbing that heat off of the engine and moving it away from the engine. So this is one of the reasons why, if you have an air-cooled engine, don't take that shield off. Don't modify that shielding and the cowling and things that are around the outside of the engine, because a lot of those components, their purpose is to direct that airflow and be able to enhance that heat dissipation and be able to get that heat away from the engine. So if you take that shroud off, the air is going to move away and not move around the engine components, and it's not going to be as effective in cooling the engine. Likewise, you want to think about what is around your engine, because I've got to have, once that heat gets in that air, I've got to have that air moving away from the engine to be able to cool that engine off. So if I put an engine in a box or build something around it, some kind of a shield or something around the engine, I'm going to be holding that air in there, and I might overheat the engine. So a lot of those things we have to keep in mind on how we use these engines and on air-cooled engines, and how the air is moving to the engine, how it's moving away from the engine, how it's moving the heat away. Now, one of the disadvantages of air-cooled engines is that I don't have a lot of ability to control the temperature of the engine. So if it's a really cold winter day, then my engine is probably going to operate cooler than if I've got a motorcycle engine in city traffic on a 100-degree day sitting at a traffic light. There's going to be a lot of heat buildup, no air moving around that engine. That engine is going to run a lot hotter than it would on a cold winter day when I'm moving down the road. So we can't control that engine temperature. And we talked about in emissions that engine temperature, the operating temperature of that engine, is pretty critical to emissions control. And so that's one of the disadvantages of air-cooled engines, is that sometimes we can't have the engine operating at the optimum temperature that we want it. So what do we do? So the other way that we control the temperature in an engine is with a liquid system, with liquid cooling. And we know fundamentally that liquid transfers the heat better than air does. So that liquid being next to a metal surface is going to pull the heat away from that metal surface a lot quicker than air will against that metal surface. So if I've got that liquid there, it's going to move it away. So the general idea is that I build a water jacket, or manufacture a water jacket into the engine, so that around all of the hot components, around the piston, around the heads, different places within that engine, there's a jacket with water in it. So ports and and chambers and stuff that I can have water and I can move that water through. What we will almost always have is some kind of a pump then that is going to force the water through that engine. So the pump will pull the water in, push it through the engine. It's going to pick up the heat from that engine. It's going to push the water back out of the engine. So now I've got this hot water coming out of there, so I need to cool that hot water down somehow. And that's where I typically have a radiator of some kind, and we'll look at radiators a little bit in detail in just a second. But that material goes into the radiator. I'm going to use a fan and some ambient air then to pull the heat away from that, and so that I have cooler air then to go back into the engine. So again, using liquid cooling, one of the advantages is, again, liquid transfers heat a whole lot better. So I can do that more efficiently and get that heat away. The other thing this does is gives me advantage of being able to control the engine temperature. So almost all engines will have some type of a thermostat in their cooling system. So we talk about that thermostat. Maybe you've had to replace a thermostat in an engine or vehicle or something. But basically what that thermostat does is it controls whether or not that cooling liquid is going to come from the engine through the radiator. So when my engine first starts up and it's cold, I'd like to bring that engine up to its optimum operating temperature so it operates efficiently, reduces emissions, and all that kind of stuff. So the way I do that is close this thermostat. That does not allow the liquid then to flow out into my radiator. So what will happen when this pump is running, it's going to be pushing water into the jacket, pulling it back from the jacket, so it's going to be cycling through the engine, but since it can't go through the radiator, it's just going to get cycled through the pump and go again. So all it's doing is just circulating the water through the engine. It's picking up the heat all the way through the engine, bringing it back, picking it up. Now, when that water gets up to the right temperature, up to my optimum temperature, now I'm going to need to keep it from going any further because I don't want to overheat the engine. That's when this thermostat will open up, and that'll allow the liquid then to go out into the radiator, be cooled off, and then come back into the engine so I can control that temperature. So again, that thermostat is pretty critical to helping that engine heat up, come up to its operating temperature quickly, and not keeping it from overheating as well. So it's got to open up in time to be able to let that cooling water go out into the radiator and be cooled down. So one of the things you'll notice on a vehicle, maybe in the wintertime your heater doesn't work very well. It takes a long time for your heater to get up to temperature. And what may be happening is that this thermostat is not operating correctly, and it's allowing this water to circulate out through the radiator all the time. And so it's going to take a long time for that to come up to temperature and be able to give you heat into your car, because your heat comes off of this water that's coming out of the engine. And so if it's being circulated through the radiator when it shouldn't be, it's going to take a long time to come up to temperature. So that's one of the things that can happen there. But again, this liquid system then allows us to better control the temperature within that engine. So both the minimum and the maximum temperatures. So that's what it is. Let's look a little bit more detail at that radiator. Again, these are typically on the front of a vehicle, but the water is circulated through the jackets, through the engine. It's pulled out. The hot water usually comes out the top, goes into this radiator. The radiator is essentially two tanks, so one on the top, one on the bottom. And then the liquid is transferred through the radiator, the radiator core, the center part we call the core. And that core is made up of a lot of really thin wall tubes, maybe made out of copper or aluminum or something like that. Those tubes are going to have a lot of fins then that interconnect them. And what those fins do is give us more surface area. So going back to like an air-cooled engine, I'm going to have air moving through this radiator to be able to transfer the heat away. But I've got now a lot of surface area because I've got all these fins. I'm spreading this hot water out, going down through a lot of different pipes. It spreads it out and is very efficient then at transferring the heat away from that liquid out into the air. And then that cooler liquid can go back into the engine and cool the engine, pull more heat away from the engine. So that's the way that cycle works. Now, of course, maintenance on these things, especially in agricultural settings, when you've got tractors and things out in dirty, dusty environments, these radiators will tend to get clogged up, that the air cannot move through. And if I can't get air to move through that radiator, it's not going to be very efficient at moving heat away from the engine. And I could end up with a situation where my engine overheats just because I'm pumping the hot water in. It's going down through. It's not getting cooled off very much. So I have hot water on the bottom that's going back into the engine. And that's not a good thing either. All right, so there's got to be some maintenance with that to take care of those radiators and think about how that whole thing works. The other thing that is pretty critical is thinking about the airflow through that radiator. And sometimes on agricultural vehicles, we'll push the air forward through there. On automobiles and things like that, where you're going down the highway, you want that air moving in from the front. The cooler air is pushing in basically because of the motion of the vehicle moving forward. So we can move that air a couple different ways. But however you do it, make sure that that stays clean and that air can freely flow through there so that that radiator works pretty well. Now, let's think about what goes into that radiator. And I kept saying water or liquid or whatever, but what do we put in the radiator? So the common solution, a common fluid we use is called ethylene glycol. And we say that that's antifreeze. You know, you've probably heard people say that. I'm going to put some antifreeze in my car. You know, I got a leak in the radiator, so I got to get some antifreeze and put in. So we think about that being antifreeze. And that's a very important property of the liquid that we put in our radiators, is that it can't freeze, because again, that water is going into that jacket on the engine and it's filling up all those spaces. And when water freezes, it expands. And so if I have water in an engine and it sits a couple days at a very cold temperature and it freezes, it could literally break and crack that engine and destroy that engine. And that's a common thing that can happen. So I have to do something to prevent that water, that liquid that's in the engine, from freezing. And so that's why we'll use some type of an antifreeze coolant that we dilute and mix into our engine. And, you know, depending on the climate that you're in, you may need more of that antifreeze, less antifreeze, and so forth. All right, so that's an important part of that's got that ethylene glycol that we typically mix in there has got to protect us from freeze. But that's really only one thing that it does. So the question then becomes, if I live in Florida and I know my vehicle is never going to freeze, can't I just put water in there? It'd be a whole lot cheaper. Well, the answer is no. You still need that fluid, that coolant fluid that goes in there, because freeze protection is only one of the things that it does. It also helps to enhance the heat transfer. So it's got some properties in it that it's even a little more efficient than water at pulling the heat away from the metal on that inside of that engine in those jackets. So it actually does enhance the heat transfer. So if you put just straight water in your engine, it's not going to cool as efficiently, and it might run a little bit hotter or maybe too hot for you. And you might have a situation where it boils over, where it boils the water and keeps pushing it out of your system. So that's one of the things that it does. It enhances the heat transfer. It actually provides some lubrication. So that pump in there, that water pump, has got a rotating shaft and it's got bearings. So that lubricant will actually give me a little bit, or that coolant fluid will give me some lubrication properties from that pump and keep that pump moving, and any other moving parts that might be in there in that coolant system, it's going to provide some lubrication for them. So that's another important thing that it does. It provides some corrosion protection. If I just put water in there, those are all metal components on the inside of that engine. They're getting very hot and cold, and that's going to make them want to corrode, make them want to rust. And if I just have water in there, it's not going to keep those components from rusting, and so I'm going to have a lot of corrosion inside of my engine and inside of my cooling system if I don't use the coolant. So corrosion protection, and then the last thing I'll mention is scale protection. So when water gets really hot, there are minerals and things in water that are going to tend to want to precipitate out, and so I'll get this scale buildup, and that's one of the common malfunctions in a radiator. When we have to replace the core in the radiator, they'll either develop a leak or they might plug up, and they plug up just because of the minerals and things that are in any water that we mix with this ethylene glycol that goes in that engine, and that scale will build up in there and plug that radiator and render it non-functional. So the coolant is going to try to prevent some of that. So keep those minerals and things from precipitating out of the fluid and clogging up the system. So it does a lot. So again, can't just put water in an engine. You've got to have the right kind of fluid, the right kind of liquid to do it. Ethylene glycol is the most common fluid that we use in our vehicles, but we're seeing, because of environmental considerations, we're seeing a lot of more biodegradable fluids, different kinds of fluids, different kind of liquids that we're using in cars. And so there's a variety of different types of fluids out there, different types of coolants and so forth, but they're all doing the same kind of thing: freeze protection, enhanced heat transfer, lubrication, corrosion protection, and scale resistance. So that's cooling systems in a nutshell. So engines get hot, we got to cool them off. Sometimes we can do it just with an air system by moving air around the outside of the engine. Sometimes we've got to be a little bit more sophisticated and have a liquid coolant system with the right kind of fluid in there to be able to protect our engines.